today is to have a tutorial on block codes. So channel coding, block codes. Okay. So assume that you have a generator matrix which is given by 1, 0, 0, 1, 1, 1, 1, 0. Okay. And then you are required to find the following. Okay. Number 1 is this a systematic linear block code. So that's the first question. Second question says find the parity check matrix. Okay. Number 3 asks you for the code words for all input messages. So basically list of all possible code words. Okay. Number 4, what's the minimum distance? Okay. So these are the questions that you need to ask. So let's look at this first of all. Is this a systematic block code? Now the idea is that for systematic block codes, G should look like I, P. Is this the case? Yes, it is the case, because we can see here that this is the unity matrix, and then we have here the rest is gonna be a parity check matrix. Now the other question says find the parity check matrix. So remember that H, the parity check matrix, is given by, so this is number 1, and the answer is yes. For number 2, the parity check matrix H is given by P transpose and then I. So in that case, we will end up with 1, 1, 1, 0, and then 1, 0, 0, 1. Right? So that's the parity check matrix. Okay. The answer to number 3, all possible code words in this case. Now, all possible input messages in this case are going to be what? We first need to figure out what's the length of the input messages, right? So remember that we have the code which is defined by K, right, and N. K is the message length, right, and N is the code word length, right? Okay, so the message length is defined by what? How would you be able to find the message length? Remember that the dimensions of G are what times what? It's N in this direction, and it is K in this direction, right? So basically, the number of rows of G is equal to the number of bits of the message, and the number of columns of G is equal to the number of bits of the code word. So we expect that the input messages are going to be combined or composed of 2 bits, right? From what we see here, because this generator matrix has only 2 rows. So if the input messages are 2 bits, what are all the possible inputs? So all the possible inputs are M1, M2, M3, and M4, and these are 0, 0, 0, 1, 1, 0, 1, 1. Now the output messages or the output code words are C1, C2, C3, C4. C1 is equal to M1 multiplied by G. This is how you get the code word, right? So if you take the matrix multiplication of M1 multiplied by G, what will you get? All zeros. So C1 is equal to all zeros. Okay. C2 is equal to 0, 1 multiplied by this matrix. When you do the multiplication, what will you get? 0, 1 times 1, 0, that's a 0. 0, 1 times 0, 1, that's a 1. 0, 1 times 1, 1, that's a 1. 0, 1 times 1, 0, that's a 0, right? Now to get C3, you need to multiply M3 as a vector with the matrix G. So 1, 0 is going to give you 1. 1, 0 times 0, 1 is going to give you 0. 1, 0 times 1, 1 is going to give you 1. 1, 0 times 1, 0 is going to give you 1. The last one is going to be 1, 1 multiplied by this, which is going to be 1, 1 multiplied by 1, 0 is 1, 1 multiplied by 1, 0 is going to give you 1 plus 0, which is 1. 1, 1 multiplied by 0, 1 is going to give you also 1. 1, 1 multiplied by 1, 1 is going to give you 1 plus 1. 1 plus 1 in XORing or in binary addition is going to give you 0. And then 1, 1 multiplied by 1, 1 multiplied by 1, 0 is going to be 1 plus 0, which is again 1. Right? So these are the possible code words that we will get out of this generator matrix, right? Now, the last question says, what's the minimum distance? Now, in order to figure out the minimum distance, what do we need to do? We can simply find the minimum weight, since this is a systematic linear block code, and the minimum weight is equal to the minimum distance. Now, don't forget that when you are taking the minimum weight, you don't consider the all zeros code word, because this exists in all code books. So we don't look at that. So the minimum weight among these ones is what? Is 2. So for W min, the minimum weight, is equal to 2. And since this is systematic linear block code, actually it doesn't have to be systematic, since it's a linear block code, then okay, D min is equal to W min, which is equal to 2. So the minimum distance of this code is 2. Okay, now based on that, I can ask you actually how many bit errors are guaranteed to be fixed. So you can tell me that any number of bit errors that's less than the minimum distance is guaranteed. So basically any 1 bit errors can be guaranteed to be fixed. I can also ask you what's the total number of bits of errors combinations that can be corrected, and that's equal to 2 to the power n minus 2 to the power k, which is equal to 16 minus 4, which is equal to 2 to the power n, it's 2 to the power 4, minus 2 to the power 2, which is 4. So 16 minus 4, which is equal to 12. So 12 of the possible error combinations, right, can be detected, right? Okay. This finishes this short tutorial, but I think looking at this, you can actually solve what you have in your assignment related to systematic linear block codes. Don't forget that if you are given a particular code word, message, and you are asked what's the corresponding code word, you can do exactly the same as what we did here to find all the possible code words. So for example, if I tell you what's the transmitted code word for message 10, then you take 10 multiplied by j, and you will tell me that the transmitted code word is going to be 1011. Also, if I ask you if you received a certain code word, for example, a question would be, what if, okay, will an error happen if you receive, okay, 1111, for example. Now, to answer this, either if you have the list of all possible code words in front of you, then if this is not one of them, then yes, an error will happen. Or the more classical way to do this, if you don't have the full list of code words, is simply to multiply this by your parity check matrix and see whether the result is going to be all zeros or not. So 1, 1, 1, 1 multiplied by h is going to be equal to 1, 1, 1, 1 multiplied by, what's our h in this case? Okay, so I was referring to, okay, just one thing that we did here, don't forget that this is H transpose. So the parity check transpose is given by PT and then I. So basically H, so this is H transpose. So basically H is gonna look like 1, 1, 1, 0. Let's make this 1, 1, 1, 0, and 1, 0, 0, 1. This is your H matrix, which is the transpose of this matrix, right? Because this is H transpose, okay? So if you do that, the result is going to be, so all ones multiplied by this is going to give you 1, because 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 0, which is 3 ones added together by XORing. So 1 XOR 1 XOR 1 is going to give you 1, and the other one is going to give you 0. So you can see that the result is not an all zero vector, which means that error will be detected. Okay, so I just added this last part to make sure that I cover all the ideas that have been discussed in your assignment related to block codes. So I hope this tutorial is going to be useful when you solve your assignment.